Sorry about that, Christine. My name's Marvin Height. I'm RF supervisor with WBNS TV here in Columbus, which is right, you see the towers right out that window if those blinds were up. And I'm a member of the planning committee for the conference. Before I introduce Christine, let me get over some of the housekeeping situations, since I know you're going to be in a hurry to get out the door right after this. Lunch will be following this across the hall where we were this morning. Be sure to visit the exhibitors. They're the ones that really pay to help put this conference on. Be sure to see them and what they have available. And they're more than happy to show you through their exhibits. Be sure to drop your business cards in the box for the drawing later this afternoon. You must be present to win. The drawings will be at the beginning of the closing general session at 3:30. And the afternoon breakout sessions, once we leave here at noon, you have till 2:30. We will resume then the afternoon sessions at 2:30. For those of you, we don't generally put it in the program notes, but for those of you who are state-registered professional engineers, Ralph is here. Ralph Thompson will make for you a certificate that is acceptable to the states for state professional development hour filings. So you can use the hours you're here today. See Ralph, and Ralph is right there in the middle of the room. See Ralph if you are a professional state-registered engineer, and I'm sure he'll be happy to take care of you. Ralph is with the Central Ohio SBE. Many of you know Christine Zuba from Dielectric. She's been here several times giving presentations, and today it's entitled Antennas and RF Equipment with ATSC 3 Considerations. Christine began her career as an antenna design engineer with RCA. Does anybody remember RCA? Yes. She's been around a long time like the rest of us. When RCA's antenna business was acquired by Dielectric, she was promoted to antenna product manager. From 1989 to 95, she was the director of sales and marketing. Currently, she manages national sales accounts and the United States Northeast Territory for Dielectric. Christine graduated from Penn State with a degree in electrical engineering and earned her MBA from Rutgers. Sorry about this coming Saturday. She is a member of the SBE and the Association of Federal Communications Consulting Engineers, and has been a featured speaker on antenna systems design, transmission lines, filter technology at regional and national SBE conferences and NS workshops, as well as our conferences here. We're pleased to have Christine today to go over the latest antenna designs for ATSC considerations.
Thank you, Marvin, and thank you all for being here. And yes, I did go to Penn State. Before we lose 2 Saturdays from this week, we're going to lose this week to Indiana, so, but I can't control that. So anyway, I'm regional manager for Dielectric, based just outside of Philadelphia. What I'd like to talk about this morning are, to follow up on that excellent presentation just a moment ago from Tom, about what Dielectric is doing in terms of the Repack, just a little bit about Repack, and then get into more of the ATSC 3.0 and how we're doing things differently in our antenna and filter designs than we were previously. A lot of people have asked, you folks have commented that you folks must be pretty darn busy with Repack. Well, this was my office at the beginning of Repack. It's a lot better now since we're now into phase 7. But yeah, you can see my hand there waving. If you were at this morning's 9 o'clock kickoff panel, they talked a little bit about the Repack and where we are and how we've been doing. We just finished up phase 6. We're into phase 7. which is January, which is not a great time of year to be doing installations. I know there's a few stations in Detroit that are phase 7. They just got 10 inches of snow or more. And of all places, Buffalo is in phase 7. So, yeah, I don't know who drew up this plan, but anyway, it is what it is. They mentioned this morning repack status, TV technology. I did this slide before TV technology report came out about 2-3 weeks ago. This was from Bill Meintel of MSW, who presented it at the IEEE Symposium in Hartford. And he took a look at phases 0 through 5. Phase 0 turned out being a lot of the T-Mobile paying stations to move early. 0.5, which was basically Puerto Rico, because once they got hit with the hurricane, they didn't want to rebuild on their old channels. The FCC gave them permission to go right to the post-repack channels. There are actually a few stations in Puerto Rico that have still not rebuilt because they can't get crews over from the States to do the install. They're so busy here in the States, they won't go to Puerto Rico. But Bill did a summary, and he categorized complete, 100% successful completion as being on their main stick, as was mentioned this morning. And you can see phases 0, 1, and 2, we did pretty well at around over 90%. As we hit phase 3, we're starting to taper off, and phases 4 and 5, a lot more stations are getting on the air with interim antennas, side mounts. And they mentioned earlier that today that this repack may go on as many as 3 more years following phase 10. Riggers are doing a pretty good job for the most part. My guess is about 12 to 18 months more following the end of phase 10 to get everybody back up to where they should be. But there's that 25% number that Bob Weller mentioned this morning of stations that are not yet on their full stick. And it's only going to get worse probably because phase 6 just completed and we don't have the numbers for phase 6. What have we been doing since the start of repack? As of November 1st, we have booked, built, or shipped 738 main antennas for repack, plus another 59 non-repacks. And we have a wideband interim aux antenna similar to what RFS was presented earlier. We call it our WB. We built 167 of these antennas, which represented 246 8-bay modules. We also have a very similar antenna for VHF that covers 7 to 13. And we have booked, built, or have shipped over 111 miles of transmission line. This is one of our two storage yards. We have over 100 antennas still on trucks, ready to roll, complete and ready to roll. Again, a lot of this is based upon crew availability and the fact that weather played a huge part at the beginning of this year, and it'll play another part as we hit. It's already playing a part as we see right now. So what are we doing for repack and 3.0? Again, the interim antenna, I showed this slide about 3 or 4 years ago when I was here last. Our WB antenna is broadband from 14 through 51. A slotted cylinder side mount antenna similar that was shown in the previous presentation. And you saw the numbers about how many of these that we've been building. Same thing for VHF. These are in 4-bay sections, so typically we're looking at a 4, 8, or 12-bay antenna. Again, side mount interims. For broadband panels, you may have heard of adaptive polarization or variable V-pol. We took our standard circularly polarized panel for multi-station applications and modified it by using 2 transmission lines and 2 combiners downstairs and phasing downstairs. You can allow, say, 3 stations operating into 1 antenna. One station can go H-pole only, another station could have 25% B-pole, a third station could have 50% V-pole, whatever they want to do. And that could change simply by changing the phasing downstairs of your channel between the 2 combiners that your power is split going into. American Tower, who has a lot of tenants on their towers, has been installing this type of system in almost every one of their sites. So what are we doing differently for 3.0 that we weren't doing for 1.0? Well, you've seen this type of slide before. 3.0 is going to mean more of everything. More signal, more platforms, more flexibility, more services, more bits. And the concept is that depending upon what kind of service, your ability to receive the signal will depend on what kind of service that you're providing and the field strength at that particular location. So if you've got a high data rate service, and depending upon how you're receiving it, if you're in a difficult location in a building that might be shielded, you might not need as high as 94 dBu to receive that signal. As opposed to a low data rate service that might be outdoor, the signal required to capture that might be as low as 64 dBu. So again, depending on the kind of service you provide and where you're receiving it, will depend on what kind of signal levels you need to get that reception. So the concept, as we saw earlier, is the big stick, and you have a lot of null fill to cover the first 5 to 15 miles, and you add SFNs around the outer periphery of your, to further saturate in those areas that are difficult to get. Now, again, these can be expensive, but the concept is that stations in a particular market will get together and combine, and you'll put broadband systems out here as SFNs for economies of scale and to save on the capital costs. This slide I showed at about 3-4 years ago when I was here last. One of the things that we're doing in all the antennas that we've been building for the last 3 or 4 years is build in this concept of future fill. Again, where you have the big stick designed for good null fill, but once we go to 3.0, if you need more signal, it allows you to go up there with a couple of riggers. They can modify the antenna, and what happens is you can increase your null fill in areas that are maybe closer in, say from 5 to 15 miles, and you increase your null fill by 7 to 10 dB. So you bring up that signal level for those 3.0 services, high data rate services. Now there's no free lunch. When you do that, you're going to lose about 1.5 dB of gain. So the concept is, if you have to do this, it's built into the antenna. If you don't need it, you don't need it. It didn't cost us anything to do it, really. A little bit of modification of the pole itself in manufacturing, but it's there if you ever need it.
And a tower crew can do it.
Yes.
It's not rocket science.
No, you open the radome up and you make some adjustments to anywhere from 1 to 3 to 4 layers on the antenna, and it pulls your null fill up. It has no effect at all on the VSWR. And again, the idea is you supplement the big stick by these SFNs. And I asked Doug Lung, I think it was at this year's NAB, from an SFN standpoint, what kind of ERP do you think those SFNs will have to have? And anywhere from 50 kilowatts to up to 200 kilowatts was his answer, depending upon what you're trying to do. So the consensus seems to be around 50 kilowatts for these SFNs. But we'll see. We'll see. So one thing we do know when we go to 3.0, it's an OFDM-based signal modulation. And we know that the peak to average power ratio will be about 2 dB higher than 1.0. So we have to make sure that when we design our antennas, we're taking that into account. Now, with the OFDM signals, one of the things that we have to take to be concerned about is that all these different carriers that are in band may add up at the same time. And if you do the math, the probability of that occurring is a 1 in 50 chance. It's basically about 2 times a year. That's not good enough for a particular design. So what we're trying to design toward when we set our safety factors or safety margins in our antennas is we're designing that for no less than 1 event in a 100-year period. So we don't want to, we want to allow that event to occur less than 1 time in 100 years. The other thing we have to be concerned about with the OFDM signal is the pulse width. There's a critical pulse width involved with the signal, and for 1.0, that pulse width is 1.315 microseconds. And this particular chart shows voltage breakdown depending on that pulse width. And for 1.0, that occurs, the breakdown is around 23 kilovolts per centimeter. And if the pulse width gets narrower, it takes more voltage to break down the RF component. And it turns out for 3.0, the critical pulse width is less. It's 0.17 to 0.18. So it goes from here up this curve. So what that means is the voltage breakdown increases. So we have an extra margin of 20% to work with for 3.0 than we had at 1.0. The other thing that we have to be concerned about, we always do for RF, is VSWR. So we have to take that into account as well. And if we put all these things together, this is our criteria. We design for a 5-to-1 safety margin on all the products that we're building. So how do we get there? Slotted cylinder antennas, which is predominant type antenna in our industry, single channel type antennas are basically steel cylinders with slots cut in them. Energy is coupled to that slot. The poles look vertical and the slots are vertical, but energy is coupled to the slot by either a bar, a type of probe, or perhaps a flat bar. We've typically used this cylindrical bar. And what that does, it couples energy from the inside of the pipe to the outside. And with this difference across the slot, the currents flow around the slot, around the pipe on the outside. That's how you get your horizontal polarization, because of currents flowing around the pipe itself. And we saw earlier how we get the vertical typically by putting that dipole above the slot. So it turns out, and with voltage breakdown and RF, it's all about geometry. So obviously, sharp edges are bad and round edges are good. So we want to make sure that, and voltage breakdown would occur right here. And how do we improve that voltage breakdown across the slot? Well, it turns out that we can get a 3 dB increase in PAPR if we double that coupler's radius. Now, if we double that coupler radius, we shorten this gap, which is not what we want to do for voltage breakdown. So what do? We go to something we called our D-shaped coupler. We double the radius, but then we cut it in half. So we maintain that same distance between the inner and the coupler itself. So we get the 3 dB increase in PAPR by doubling the radius of that coupling device. And we've been doing this now for about 4 years in every antenna we're building. For panel antennas, typically panel antennas can be fed in a couple of different ways. You can use a coaxial system, or you can use a strip line type feed, which is a little bit simpler. But again, the strip line will have sharper edges that you want to avoid. These pictures here depict a high-frequency simulation software look at the heating and the breakdown that occurs using a microstrip type feed system versus a coaxial type feed system. HFSS is commonly used, been used for many, many years in the microwave industry, and over the last 10 years it's been used more and more in the broadcast side for design. Virtually everything we're doing now is HFSS designed. And so here you see the heating that occurs with the strip line type feed. Well, I don't see. There it is. With the strip line versus a coaxial feed. So for the high power 3.0 applications, we're using coaxial feeds. And it turns out that if you also pressurize the feed system, you can get this 50% increase in the voltage safety factor, which means another 3.5 dB increase in the PAPR margin. So for all of our 3.0 ready systems, we're using coaxial feed systems, and obviously they're pressurized.
Say what PAPR is, please.
Peak to average power ratio. So from an antenna standpoint, 3.0 means we have new things to consider. Voltage breakdown, co-phased voltage additions for the OFDM signal, pulse width, and we have to pay attention to geometry. If we combine all these, which we've been doing now for forever, basically, we can have product that's available for 3.0, and we do. Let's shift over a little bit toward filters and combining. Again, we know there's the higher PAPR to deal with. The other thing we have with 3.0, which we didn't have with 1.0, is about 0.5 megahertz more bandwidth to be concerned about. And because stations will be using VPOL, that increases the power downstairs. I'd say probably 90% of all the antennas that we're building for Repack have vertical with them, anywhere from 25% or more. Those stations that choose not to do the VPOL, it's primarily for economic reasons. They didn't want to pay the extra transmitter cost. The cost for doing VPOL in the antenna is minimal. It's about 10 to 15%. The cost from going from a 40 kilowatt box to a 50 kilowatt box can be $1 million. So that's typically why stations have not chosen to go VPOL if they have. So we know that we have a little wider bandwidth to worry about, but if you've got a 6-pole filter, and you've probably heard this now forever, if you've got a 6-pole filter, it'll work. Combination of the filter performance and the transmitters will allow that to do so. 8-pole filters are typically used where you have adjacents in the market. And the bottom line is here, where a transmitter with a 6-pole filter will broadcast 18 dB more noise into the adjacent channel than will an 8-pole mask filter. So that's why we're doing 8-pole masks when there's adjacents. Now, even though there may not be high power adjacents in your market, there might be a low power adjacent. So think about that 18 dB more noise when you're at 1 megawatt and there may be a low power adjacent 20 miles away at 15 kilowatts. That's a lot of signal getting into their channel. So if you're a 1 megawatt station operating near a 15 kilowatt low power, your sphere of influence to that station can be fairly large, whereas if you go to an 8-pole filter, that sphere of influence is reduced. So you're causing much less interference with an 8-pole filter into a low power adjacent. When we start talking about adjacent channels, for 1.0, because of the slightly narrower bandwidth, we had 620 kilohertz guard band between the two channels. At 3.0, we only have 160 kilohertz. So that's a much difficult challenge when we talk about adjacent channels. So if you look at a typical response of an 8-pole filter in an adjacent channel type combiner, you can see the roll-off that starts to occur. This engineer was kind of funny when he did this slide. Now, the transmitter will try to compensate for that roll-off. You also have additional group delay using an 8-pole filter, but again, this is for today's transmitters, it's really not a problem. We start talking about channel 14s. We're doing 12-pole filters because of the land mobiles. That's quite a bit of group delay involved there. But even with that kind of group delay, the transmitters can handle it. The thing we have to be concerned about when we get involved with adjacent channels or any 8-pole filter are the voltages that are occurring inside those filters. And it turns out that if you put 1 volt in an 8-pole filter, you could have up to 23 volts at the band edge. So that's quite a factor of multiplication there. And that's just with 1 volt. And because of that roll-off of the pass band, the transmitter is going to try to compensate for that and pre-correct to try to flatten that response. So again, you're going to have more power at the band edges that you have to worry about. Turns out that all of this energy occurs in the last 2 sets of resonators in the 7 and 8-pole filter. So that's the area we have to be concerned with. So if we look at a typical half wavelength cavity in an 8-pole filter, where you might have 2 adjacents, a channel 19 and a 20, each running 40 kilowatts. Again, this is a HFSS analysis, a heating analysis of the heating that occurs around these probes. You can see blue is cool, red is hot, as we've seen before. With only 40 kilowatts applied, these probes are running fairly cool. However, if we turn the other adjacent on, and we now have both channels at 40 kilowatts, you can see what's happening at these probes. Pretty darn hot, which is not a good thing. So how do we get around that in an adjacent channel combiner? We go to a full wave cavity in those last 2 resonators. By going to a full wave cavity instead of a half wavelength cavity, that heating goes away. And we get a 2-to-1 improvement in the voltage safety margin. So typically an 8-pole cavity will have 3 sets of half wave cavities, and then the last 2 resonators will have a full wavelength. The other way to get around this is to use rectangular waveguide filters. They are a little bit more expensive, but they do handle more power, upwards of 100 kilowatts. Now you might think 100 kilowatts is a lot of power in today's world. There are some systems out there that are running 50% or more VPOL at 1 megawatt Omni. So you're talking about 60, 80 kilowatt, close to 100 kilowatts of power, particularly some using low gain antennas. The rectangular filter, what it gives you is two modes of adjustment. You can adjust the tuning in a waveguide cavity by the probes on the broad wall, also by using panels on the narrow wall. So you can adjust with the probes and the panels. So you have two ways to tune the rectangular filter. And what that does, it minimizes the heating that's occurring at the probes themselves, at the tuning probes. This is just an example of the kinds of things we're doing on the combining side. This is Detroit. ATC tower, some of you might know the tower. It's got three, it's a candelabra. It's got 3 separate antennas on each of the arms. One of the stations, I think it was WMYD, was a phase 2. The other 2 channels were phase 7. So it's a tower owned by American Tower. What they did is they put in a broadband, one of our WB antennas on the side, and that allowed everybody to go into that WB antenna. But what we had to do for American Tower, we had to design a combiner that would handle all 3 of the pre-repack channels and all 3 of the post-repack channels. Because the one station was phase 2, so they had to change early. The other 2 channels are phase 7. They're getting ready to change in 10 inches of snow. So everybody had to go onto this aux system back in phase 2. WMYD had to change their antenna out. Everybody went back up to the top. And then come phase 7, everybody's going to go back on the interim antenna. They'll do the work on the top of the tower to get rid of the other 2 antennas, change them out. And then this system had to be ready to handle the 3 post-repack channels as well. So it would stay as a permanent aux. So these systems can get quite large. And this is a large system, but again, for what we're doing, it was relatively small with the filters and the switches involved. So basically, these get built in the factory, taken apart, they get through the building door, and then reassembled on site. So we think about the antennas and the transmission lines and single channel filters. We forget about the complexity of a lot of this stuff inside the building. So from a filter standpoint, 6-pole filters work. 8-pole filters are needed where you have an adjacent in the market or perhaps a low power outside the market. 3.0 means a little wider bandwidth, higher PAPR, higher transmitter power for the VPOL. And if we take all these things into account, there are ways to design for it. You just have to take those into account going in. Now, a lot of people have asked, what are we going to do after the repack? Aside from retire one of these days. One of the things that we're looking at, we know there's fewer and fewer groups with more stations per group. And the number of qualified RF engineers is not increasing. It's actually, we know it's going down. So service is a big word these days, both from an RF standpoint, from an antenna manufacturer, and from a transmitter's point of view. So one of the things we're doing is we introduced this at NAB. We call it our RF Hawkeye. It's a real-time monitoring TDR approach where you can monitor the discontinuities in the transmission line without breaking the line. So you set this system up. You can take a look at all the joints. in the transmission line run. And this was an older system, so this is not a new run, but this was an older system. And then you could set your parameters so that if any of these joints start to approach the limits that were set, alarms are sent out so you could get in there, break the line, start taking a look. And I believe we can identify a discontinuity within plus or minus a couple of feet in the line. It may be even better than that. So we're seeing a lot of interest in this product. So again, it's something we're doing looking toward the future. And that's it. Thank you for being here. Is it lunchtime? Any question? Question?
That TDR system, that is a dark measurement, isn't it? I mean, you're not on the air when
Yes, you are. Yes, you are. You're on the air. You don't have to go off the air to do it. Yeah. What it does, it's a extremely low power VHF signal that's sent up the line. So this right now is only for UHF. We're developing it for VHF and for FM. Right now it's just for UHF. But it,
TDR works at an entirely different frequency range
yes.
than on air.
Yeah. Yeah. Yeah, you don't have to break the line. That's the benefit of it.
What's the going price for that knockout?
It's around $22,000.
That's not bad. My question was going to be, was it available for FM?
Yeah, I know we've seen a lot of interest for FM. That's in the works.
How many did you bring?
Let me open my trunk. So,
We'll just charge it tomorrow.
What's it? Oh, yeah, charge it to me. Any other questions?
thank you very much.
Thank you, Christine, for being with us today. Last housekeeping item, and we beat the lunch trail next door. Last housekeeping item is that recordings and slide presentations will be available in the next couple weeks at the oab.org website. You can download for your own use. Okay? Thank you all very much. Wow.